Welcome back to the deep dive. Today we are getting foundational, really digging into networking 104, how digital systems are physically built and, how they communicate.
Yeah, and this is essential stuff.
Absolutely. I mean, if you're responsible for maintaining or designing massive infrastructure, like the systems you'd see at a roadway traffic management center or RTMC, this is the base layer you have to know.
And our source material today is extremely specialized. This comes straight from an Intelligent Transportation Systems masterclass on networking.
Oh, wow.
It was developed and presented by AtkinsRealis, specifically for the Florida Department of Transportation. So this isn't just theory, it's the real-world operational knowledge they use to keep traffic systems, cameras, everything connected.
Okay, so our mission today is to really get a handle on two core pieces. The physical blueprint, what's called network topology, and then the rules of the road for data, which is Ethernet. We're going to pull out some key nuggets on why things are built the way they are and how it all works.
And just to ground ourselves really quick, from our past sessions, remember layer 7 of the OSI model. That's the application layer, where you as the user interact.
Right, and layer 4 is transport.
Exactly. But today, we are going all the way down to layer 1, the physical layer, and how all that hardware is actually put together.
Let's do it. So topology. When we talk about topology, we're talking about the layout, the configuration of the systems, and the path data takes.
Right, but there's a really critical distinction to make right away. Topology actually has two different functions.
You mean it's not just about where the cables are?
Exactly. You have to separate the physical topology from the logical topology.
Yeah.
The physical is layer 1, the cables, the connectors, where the hardware actually sits.
Yep.
But the logical topology is how the signals actually travel electronically, which can be totally different. The wires might look like a star, but the data might be moving like it's on a bus.
That's a great point. Okay, so let's start with the basics then. The oldest one that you might still run into, bus topology.
Bus is the simplest. I mean, you just have systems connected in a line on a single cable. This dates all the way back to the 1970s, to the birth of Ethernet.
So data just gets sent out and every machine on that cable sees it.
It's broadcast, yeah. Every single host looks at the message to see if it's for them. But there's a physical catch. The cable needs what's called termination on each end.
To absorb the signal, right, so it doesn't just bounce back down the line and cause chaos.
Precisely. The pros are, well, it's cheap on cable and easy to set up initially.
But the cons seem pretty brutal, especially for something like an RTMC. I mean, you've got a massive single point of failure.
Huge. Cut that cable anywhere, and the whole network is dead. Plus, every device is on one big collision domain, fighting for that sliver of bandwidth.
And that fight continues with the next one, right? The ring topology.
It does. With a ring, data travels from system to system in a circle, usually just one way. And since it's a closed loop, you don't need termination.
But that single point of failure problem is still there, isn't it? If one machine in the ring dies.
The whole data flow stops. The entire loop is broken. Unless you've paid for a much more expensive bidirectional routing.
And that structure is a perfect example of a term we hear a lot. Daisy chaining.
Daisy chaining is a great way to put it. It's exactly that data hopping sequentially from device A to B to C until it finally gets where it's going.
And every one of those hops adds a little bit of delay, and it makes troubleshooting a nightmare.
A total nightmare, because every device in that chain could be the source of the problem.
So if bus and ring are so fragile, the answer, especially for critical infrastructure, has to be the star topology.
Star is the model. It's what almost every modern network is based on. All your systems connect directly to a central piece of hardware, like a switch.
And here's the key nugget, right? For anyone managing infrastructure, the fault tolerance is just phenomenal.
It is. If one cable going out to, say, a traffic controller gets cut, the other 99 controllers connected to that switch are completely fine. They just keep working.
That immediately seems like the clear winner. But you're just shifting the vulnerability, aren't you?
Yeah, you absolutely are. The single point of failure now becomes that central hub or switch, if that goes down.
The whole segment goes with it.
Which leads us to the final wired setup, which is what most large systems actually are, a hybrid topology.
Just combining two or more of the others.
And the most common one you'll see is a star bus. You have a bunch of individual star networks all connected to each other along a central bus backbone.
Which gives you that local fault tolerance, but you still have to worry about that main backbone.
And those central switches in the stars can become bottlenecks if they get overloaded. You get redundancy, but the complexity and the maintenance get a lot tougher.
Okay, quick shift to wireless. When we're talking about big wireless setups, sensor arrays, things like that, we're almost always talking about mesh topology.
Mesh is basically redundancy on steroids. In a fully meshed network, every single device has a direct, unique connection to every other device.
So if one path fails,
There are dozens of other paths for the data to take. It gives you incredible reliability and fault tolerance. Think of all the ITS sensors along a highway.
but I'm guessing that level of redundancy is not cheap.
It's high cost and very high on processing power. Managing all those routes is complex. Your network hardware has to be constantly calculating the best path, which is way more intensive than a simple star network.
So we've got the physical layout. Now for the really crucial part, the rules they all use to communicate. And for local and wide area networks, that pretty much means one thing.
Ethernet. It is the universal language. It's what you use at home, at the office, and it is the absolute backbone of the FDOT RTMC.
And it completely took over, right? It wiped out competitors like IBM's Token Ring.
It did, and it's because of one single, frankly, brilliant strategic decision.
I love this story. It starts at Xerox in 1973, just trying to connect office computers. Pretty slow, like 3 megabits per second.
Right. Then by '79, Xerox teams up with Intel and Digital Equipment Corporation, the DIX standard, and they bump it up to 10 millips.
But here it is, the aha moment. In 1983, these 3 corporate giants decide to transfer control of the Ethernet standard to the IE.
The Institute of Electrical and Electronics Engineers. And this was revolutionary.
By making Ethernet an open standard managed by the IE 802.3 committee, they basically laid the foundation for the entire digital world.
It's not an exaggeration. It meant anyone could build switches and network cards that were guaranteed to work with everyone else's.
If they hadn't done that, imagine a world where only IBM could make networking gear. Companies like Microsoft or Apple, they never could have scaled.
Exactly. And that open standard is what defines the crucial functions we rely on. Let's start with the containers that actually carry the data, frames.
These are layer 2 containers, and they have to be a very specific size, right? A minimum of 64 bytes and a max of 1,518.
That's right, and for a good reason, because inside that frame you have important sequences like the 7-byte preamble and the 1-byte start frame delimiter, the SFD.
The preamble is like the get ready signal.
It is. It alerts the receiving network card that data is coming. And the SFD is the go signal. It marks the absolute beginning of the meaningful data. That structure is vital for reliability.
We also need efficiency. That's where duplex modes come in. Half duplex means you can only send or receive at one time.
Like a walkie-talkie.
Exactly. Versus full duplex, which is simultaneous sending and receiving. Modern systems are pretty much always full duplex.
And the hardware managing this flow, that's the real difference between a fast network and a slow one. We're talking hubs versus switches.
A hub is, well, it's pretty dumb. It gets a signal on one port,
And it just blasts it, broadcasts it out to every other port.
whether they need it or not. So physically it's a star, but logically it acts like that old, inefficient bus.
That lack of intelligence is why switches completely replace them. A switch is smart. It learns the unique MXC address of every device connected to it.
So when data comes in for a specific device, it sends a unicast signal.
Only to that one target port. It's targeted, it's efficient, it's faster, and it segments the network.
And let's clarify those casts, because for a system like an RTMC, it's not all one-to-one.
Not at all. Unicast is that one-to-one communication. But something like an RTMC relies heavily on multicast.
Okay, how so?
Think about a video stream from a freeway camera. Instead of sending a separate unicast stream to 10 different surveillance desks, you send one multicast stream that all 10 can tap into. It's way more efficient.
Compared to broadcast, which goes to absolutely everyone on the network segment.
Right, which is usually just for things like network discovery protocols.
So to keep all of this traffic from just crashing into itself, Ethernet came up with another brilliant protocol, CS-MAS-CD.
Carrier sense multiple access with collision detection. It's basically the traffic cop for your data.
Okay, break that down. First part, carrier sense.
The device literally listens to the cable. If it hears traffic, it's busy. It waits a few milliseconds, checks again. If the line is free, it sends its frame.
Then multiple access.
That just means everyone has equal access. If the line is free, it's first come, first served.
And the most important part, collision detection. What if 2 devices send at the exact same instant?
They both detect the collision. It's a jumble of voltage on the wire. They immediately stop transmitting, and then they each generate a random back-off number.
A random amount of time to weep before trying again.
And because it's random, it's extremely unlikely they'll collide on the next try. It keeps the network from getting stuck in a loop of collisions.
This defines the whole concept of a collision domain, the group of nodes that can collide with each other.
And here's the crucial takeaway from the source material for anyone managing infrastructure.
Yeah.
On a modern switch, each port is its own collision domain.
So switches basically eliminate the collision problem by design.
They minimize it dramatically. The final piece of Ethernet's genius is its adaptability. We're talking auto-sensing or multi-speed negotiation.
This is huge because you've got equipment from different eras, a brand new 10 gig router and an old 100 megabit controller.
And this function lets them talk to each other. They automatically figure out the highest common speed in duplex mode. They can both support and agree on it.
So that 10 gig router and a 100 meg switch don't just fail, they negotiate down and communicate perfectly at 100 megabits per second.
It's absolutely essential for backward compatibility in large evolving systems.
And that evolution is constant. That's why the IE 802.3 committee is always working. Technology just gets faster.
It does. And you can decode the standards from their names. Let's use 10 base T as an example.
Okay, so the 10 is the speed, right? 10 megabits per second.
Right. Base means it's a baseband signal, just one data stream. And the T tells you the cable type.
T for twisted pair copper cable. F would mean fiber.
Exactly. And the progression tells a story. We started with 802.3i, or 10 base T, back in 1990, 10 Mbps over C23 cable.
But then just 5 years later, a massive jump.
A huge jump. 802.3u, which was 100 base TX. Everyone called it fast Ethernet.
A tenfold speed increase to 100 Mbps. This is when we got the RJ45 connectors and C@Fate5 cable we still use today.
And this standard is what drove the need for that multi-speed auto-negotiation, because organizations had this huge, expensive task of upgrading all their old wiring.
Then came the gigabit era in 1999. 1,000 base T, 1 gigabit per second.
But for an agency like FDOT, speed isn't the only issue. Distance is everything.
Right. Copper cable maxes out at 100 meters. That's not going to get you very far down a highway.
Not at all. And that's where fiber standards are critical. You have 1,000 base SX on multi-mode fiber, which gets you about 500 meters.
But the one the department uses most, according to the masterclass, is a Wisen base LX.
That's the one. It uses single-mode fiber to push a 1 Gbp signal up to 5,000 meters.
5 kilometers, that's over 3 miles.
And that immense reach is what lets the RTMC connect to a controller at a distant intersection or a sensor site way down the road, is what makes the whole system work over a large area.
So really, the backbone of any current system requires everything to be speaking that 100 and 100 1,000 auto-negotiation language to keep things running smoothly.
It's non-negotiable. Understanding why you use a star or a mesh over a bus or a ring, and knowing how Ethernet manages traffic, those are the foundational concepts.
So we've covered the basics of the physical layer. The source material says the next step in this masterclass is Networking 105, all about practical application.
And then a deeper dive into electrical training. And for those who want the really hardcore networking knowledge, they're planning a 201 series on things like OSPF, VLANs, and the big shift from IPv4 to IPv6.
It's a huge field.
It is. But let's leave you with a final thought. Think back to that decision in 1983. Xerox, Intel, and Digital, they chose an open standard over proprietary control. It triggered an explosion of growth.
It enabled everything we have today.
So the question is this: what critical underlying communication technology are you relying on today that is still locked down by a single vendor? In transportation, in medicine, anywhere.
And what would happen if that technology were suddenly made open?
What massive industry-wide leap forward might that trigger next?
That is some real food for thought. Thank you for joining us for this deep dive into the infrastructure that keeps our world and our roads moving. We'll catch you on the next one.